So the algorithm that we're going to look at for solving the substring search problem is called the Knuth-Morris-Pratt algorithm. It's got an interesting history that we'll get to at the end. But I just want to start by saying that this is one of the coolest algorithms that we'll cover in this course. And it's not an algorithm that anyone would come up with without a lot of hard work. But understanding this algorithm really gives somebody an appreciation for what's possible with careful algorithmic thinking, even for such a simple problem as this. It's a quite ingenious method. So here's the intuition behind the algorithm. So say we're looking for the pattern B followed by a bunch of A's in text. So we're going along, and so, well, we found a mismatch right away, so we'll move over to first position, and we'll go B, A, and we find a mismatch at the end in this case. So now what the brute force method is going to do is back up to move over one position, that B doesn't match the A, back up again, that B doesn't match the A, and keep going, matching the first B against all these A's before getting to the next character in the text. So we match 5 characters and we mismatch on the 6th. But the key point is that when we got that mismatch, if all we have is A's and B's, we already matched B, A, 4 A's, and we got a mismatch, so it's a B. So at that point, we know what the previous characters in the text are. And we know that if we move over one position, we're going to be trying to match B against A. So we should be able to take advantage of that knowledge. That's the intuition on the method of the Knuth-Morris-Pratt. We don't need to back up the text pointer in this case. When we get the mismatch, we can just keep going. We don't even have to match the first B. We know it's there. So we can just keep going in the text pointer and start in the second pattern pointer. The Knuth-Morris-Pratt algorithm is a very clever method that manages to always avoid backup, no matter what the pattern is. So let's take a look at what's involved. It's based on the idea of building a deterministic finite state machine for string searching. Now, deterministic finite state machine, if you're not familiar or don't remember, is a very simple thing. It's got a finite number of states. It's always in one of the states. There's a start state and a halt state. And from every state, there's exactly one transition for each possible character in the alphabet. So if we're in a state and we're reading a particular character, we move to the state that is indicated by that character. So if we're in state 2 and we're reading an A, we move to state 3. That's what this line in the table says. If we're in state 2 and we read that happens to be the pattern character is A, if we see an A, we move to state 3. If we see a B or a C, we go back to state 0. That's what this machine says. This is a tabular representation and a graphical representation. If we get to state 6, then we just say accept. We found the pattern. And you can see how that is. The pattern, if we match a pattern character, we move right through this machine until we get to the halt state. So let's first take a look at exactly how the machine works to make sure that everybody follows that. And then we'll look at how do we build this machine. So that's our machine, and that's our text up at the top. So we start in state 0. We're reading an A. What are we supposed to do? If we're in state 0 and we read an A, this entry of the table says we're supposed to go to state 1. So we go to state 1. At every step, we consume a text character, just read a text character. Now we're in state 1 and reading an A. In the graphical representation, it says stay in state 1. Or in this representation, that says if you're in state 1 and you see an A, stay in state 1. So that's what we'll do. We'll read the A and stay in state 1. Now we're in state 1, and so you could say that in in state 1, it's reading A's and looking for something that's not A. And no matter how many A's you have, you'll read them right here in state 1. So now we're in state 1 and we're reading a B, and it says go to state 2 in that case. So that's where we'll go and read the B. Now we're in state 2 and reading an A, so we go to state 3 and read the A. Now we're in state 3 and we see a C. In state 3 and we see a C, we're supposed to go back to state 0. That's a mismatch. Our pattern, the C is not until the end. So now we have to start the search all over again. Although in the finite state machine doesn't know that, it's just plotting along according to the state transitions it's supposed to do. So we read the C, now we're back in state 0. So now we're in state 0 looking at an A, and we move to 1 and read the A, and then we see another A, so we stay in 1 and read the A, and now we see a B, and we go to state 2 and read the B, and then we go to state 3 and read the A, state 3 and read the A, state 4 and read the A, state 5 and read the C, and now we're in state 6. That means we found the pattern. So that's a simulation of what the deterministic finite state automata corresponding to this pattern would do. And as we'll see, the code for implementing this simulation is quite simple. That's a demo of DFA simulation. So let's just take a quick look at what the interpretation of this DFA is. So what does it mean after we just read the ith character of the text? Well, the number of the state is the number of characters in the pattern that we've matched up to the current point. So that is, at state 3, we've matched 3 characters in the pattern. And what's happened is that we've matched a prefix of the pattern, the first 3 characters of the pattern. And actually, it's the longest prefix of the pattern that's also a suffix of the first I plus 1 characters of the text from 0 to I. That's the interpretation of what it is. So if the DFA is in state 3, after we read the first 6 characters of the text, it's got ABA is the longest prefix of the pattern that's also a suffix of the first 6 characters of the text. So another prefix of the pattern that looks like it might work is ABABA, but that's not a suffix of the text, ending at character 6. And so that interpretation is useful to understand what's going on. So given that we've constructed this DFA, it's just the state transition table for the DFA is simply a 2-dimensional array that's indexed by the pattern character. So if you're in if you're reading a certain pattern character, if you're reading a certain text character, then for each, we reset the pattern pointer to be the entry given in the table that corresponds to the current one. So let's go back to the table to be sure about that. So when we're in a particular state, like 2, and we see an A, so this would be J, we refer to that column and whatever text character we happen to see, that's how we update J. So that's what this code does. And then if we ever get to the transition state, the final state, we just return I minus m. This is just like that alternate implementation of the brute force method that we gave, but the key idea is that notice that I never gets decremented. All we're doing is incrementing I and changing J. Always just referring to the table. When we have a match, the table automatically increments J. We have a mismatch, it figures out the right state to go to. So that's a very simple and economical and fast implementation of substring search. So the running time is clearly, all it does is look up an entry in the table for every text character. So that's linear time. The key is, how do we build that table that drives the algorithm? And that's the tricky algorithm. So warning, this is definitely the trickiest algorithm we've looked at so far. And the key idea, the importance again of no backup is that since the text pointer never decrements, you could use an input stream and just replace text divide by just read the next character in the input stream. And this algorithm is going to work fine no matter how big the input stream is. It'll just go right through. It's got no memory of what the text is, but it's got some memory of what the pattern is that's built into the DFA. So this is the key, that you have a pattern, you can spend some time building this DFA table in pre-processing, but then when you get the text, just index into this table for every text character, and you're doing your substring search. So you can build a machine that does this, no backup. Okay, so let's take a look at what it means to construct this DFA. So it depends on the pattern. You start out with one character, one state for each character in the pattern, plus an extra except state. And let's look at what it means to build the thing. So the first thing that we do, so one state for each character in the pattern. The first thing we do is deal with the match transitions. So that's when you're in state J. That means you've already matched J characters in the pattern. Then if the next character matches, so the character that you have is the character that's supposed to match, you're going to, so it's that caret J, that's the J plus first character, then you know that you've matched J plus 1 characters. So all that means is we can put in the match transitions. So we have A, B, A, B, A, C, and these guys go A, B, A, B, A, C. If you're in state 0 and you see an A, you go to state 1. If you're in state 1 and you see a B, you go to state 2, and so forth. That's how we get the match transitions to get us all the way through the pattern to the accept state. So that's the easy part. And then the hard part is the mismatch transitions. What are you supposed to do if you come against a text character that does not match the current text character? So, for example, if you're in state 0, the pattern starts with an A. If you don't see an A as the first character in the text, if you see a B or a C, then obviously you want to stay in state 0. So you can think of state 0 as scanning through the text looking for an A. It's going to stay in state 0 as long as it sees a B or C. As soon as it sees an A, it'll go to state 1. But that completes state 0. You know what to do if you have an A, you know what to do if you have a B or a C. What about state 1? So we know that if you're in state 1, you saw an A in the text, and if you see a B in the text, what are you supposed to do? Well, there's two different cases. If you see a B, you go on to state 2. If you see a C, then that's not going to match the first character A in the pattern, so you go back to state 0. But if you see an A, it's just as if you saw an A in state 0, so you might as well stay in state 1. So that's how we fill in the DFA for state 1. If you see a B, you go on to state 2, you matched. If you see an A, well, that matches the first character, so stay in state 1. If you see a C, clearly you have to go back to state 0. Okay, what about the next one? If we're in state 2 and we see an A, we know that we go on to state 3. And what about the mismatch cases? Well, in that case, it's a B or a C, and again, if you're sitting on a B or C, you better go back to state 0 to keep looking for an A. State 3, well, now it gets to be a little more complicated. C, you state 3, if you see a B, you succeeded. If you see a C, you go back to state 0. It's not so bad. If you see an A, it's just like before. That's going to be like the first one. So it seems like we're going along pretty fine. And again, if you're in state 4, you see an A, you go to 5. If you see a B or C, then you better go back and look for an A again. This one is the one that's a little more complicated. If you're in state 5 and you see a B, you go back to state 4. And that's a little more work to figure out why that's the case. And that last case is kind of the essence of the algorithm. So we'll look at a systematic way to be able to figure out what you do on a mismatch in each case. In this case, you only needed that for that one state. Otherwise, it was elementary reasoning. So that's the full DFA for Knuth Morris Pratt, a demo of at least thinking about how it's going to be constructed. Okay, let's look a little more carefully and systematically at the construction process for the Knuth Morris Pratt DFA. So the start is clear. We're going to go through the pattern and systematically fill in the match transitions. If we're in state 0 and we see an A, we want to go to state 1. If we're in state 1 and we see a B, we're going to want to go to state 2. State 2, so we look up the pattern character, and then whatever that one is, we want to go to the next state. So we can fill in at least that much automatically. Now the real key is the mismatch transitions. So here's the idea of the mismatch transition. So if you're in state J and you get a mismatch, the next character in the text does not match the jth character in the pattern. So as pointed out at the beginning as motivation for Knuth Morris Pratt, you know a lot about the text at that point. You know that the last J-1 characters of the text are, if you lop off the first character of the pattern, it's from 1 to J-1. So in this case, and then it's followed by the text character that you're looking at. So one thing that you could do, so what you want to do, so you know that, and what you could do is simulate the DFA that you have built on that part of the pattern, and then take the transition for the character that you just find. So let's look at this. So let's run this machine. If we had seen it on the text BA, that's what we want to do. We want to put the machine in the state as if we had backed up, but we don't want to back up. So if we see a B, we stay in 0. If we see an A, we go to 1. Then we see a B, we go to 2. And if we see an A, we go to 3. So now we're in state 3. And if we had a mismatch, then for the fifth character, what we do on a mismatch here, we have to look at what happens if we get an A or if we get a B. If we run it on BA and we got an A, then we should go back to 1. So what that says is if we had a mismatch and we saw an A and 5, we would need to be in state 1, because if we had run the thing on the characters that we know, BA, A, we would wind up in state 1. And similarly, if we got the mismatch on a B, again, if we did BA, we'd be in state 3, and we're in state 3 and we saw a B, we'd go to 4. So again, to summarize, if we're in state 5 and we see a C, we know that's a match, we go to 6. If we see an A, we know that the previous 5 characters in the text were BA, A. So we can just simulate the machine, BA, and we're in state 1. And if we get a mismatch that's a B, then that's DFA B5, then we know that the previous 5 characters in the text were BA, BA, B, and that would put us in state 4. So that's the simulation of BA, BA puts us in state 3. If we get an A, we go to 1. So that means that from 5 we would go back to 1. And if we get a B, we go to 4. So that's how, one way to calculate the mismatch transitions. And as we noted in the simulation, this is the only non-trivial one for this example. Now there's a little problem with that, is that it seems to require J steps to do the simulation. In order to figure out these mismatch transitions, I had to go all the way through the pattern shifted over one to figure out this state 3. So that seems to be a bit of a problem. But actually it's no problem at all, because we can run this simulation one character at a time as we're building the machine. All we need to do is keep track of the state that we would be at if we had run the DFA on the pattern starting at position 1. Once we get going, it's pretty easy, but just let's start, let's illustrate it by saying, okay, we maintained the state X, which is where we would be if we had run the machine on the pattern shifted over 1. Now, when we come to do our mismatches, to figure out where the mismatch transitions from 5 are, all we do is look at, if we were to get an A, it would be as if we were in state X and got an A, so that's 1. And if we were to get a B, it would be as if we're in state X and got a B, and that's state 4. So what we need to do is to compute the mismatch transitions is keep track of state X, and that is where would the thing be if we had run it starting with at the pattern 1 position shifted over. And we want to update that. So when we're moving to the next state, if we had a match on C, state X gets updated to where it would have gone if it got a C, because for the next character, when we move J over for the match on C, we'll want to have X updated. So that's the key, is keeping track of the state where the machine would be if we had backed up, or if we had run it on the pattern shifted over 1. So let's take a look at a demo that does the full construction for the KMP DFA. So here goes. Again, 1 state for every character plus an except. Match transitions are easy. We build those, and we're going to start at position 0, and the mismatch transitions are easy. So now when we move over, X is, when we're in position 1 of the pattern, X is where we would be if we started out without that character, which would be the empty string. So we start out with just filling in zeros. For state 0, and we can do that without any further reasoning. But now we've got X initialized. So now what we need to do is fill in the mismatch transitions for state 1. So what are they? They're what would happen if we found those characters and we were in state X. If we found an A, we'd go to state 1. If we found a C, we'd go to state 0. And maybe you notice that's just taking the entries corresponding to the entries we need from X's column and putting it in J's column. That's all it is. And then we need to update X, which is where it would be if we matched a B. So we'll stay in, X will stay in state 0. So now let's look at state 2. So we need to fill in what would happen if we got a B and what would happen if we got a C. Well, it's what would happen if we were in state X and we got a B or a C. So all we do is move those 2 zeros over to column 2. And then don't forget we have to update X, and X goes where the machine would go if we saw an A, that transition from 2 to 3. So we just move X to state 1. So now we have X in state 1 and we're doing position 3. And now you can see how really simple the algorithm is once it gets going. Now the mismatch transitions are A and C, and that's what we have to fill in for column 3. But those mismatch transitions were already computed. That's where X would go. That's where it would go if we happen to be in state 1. So we move the 1 and 0 from column 1 over to column 3. And again, we update X. And when we see a B, X goes to state 2. And again, you can check what is X supposed to be. It's supposed to be where you would be if you started the machine on the pattern with the first letter cut off. So it's supposed to be where would you wind up if you got BAB, and that's a check. All right, so now it's straightforward. State 4, we have to fill in B and C. We go to X's column and copy over B and C from X's column. Then we update X. That's if you see an A, you go to state 3. Now we're ready for state 5. We've got X all computed. And we need to do A and B, and we get those from X. If it's an A, it's a 1, and if it's a B, it's a 4. It's just moved them over. And then when we do the C and get the accept, there's no mismatch. We do update X to get ready, but when we get to state 6, we're done. And again, it's just as a double check, X is where you'd be if you saw B, A, B, A, C. That's the construction of the Knuth-Morris-Pratt DFA. An efficient algorithm, really ingenious, and turns out simple to implement. Implementation for the DFA construction for Knuth-Morris-Pratt requires remarkably little code. So it just goes through what we did in the demo. So we've got X, and for every entry of the DFA in X's column that corresponds to everyone except for the match, we just copy X's column to J's column. In fact, we just copy them all and then overwrite the one corresponding to the match case to J plus 1. So the entry in the column that corresponds to the pattern character, that's where do we go if we match, that's J plus 1. All the rest of them are copied from X. So one for loop to copy from X, then set the match case. And then the only other thing to do is to update X. And how do you update X? You take the machine to where it would go if it were in state X, and it got the current pattern character. So that's the DFA construction, amazingly little code. The only flaw in this code is that it does take time proportional to R times M, where R is the radix and M is the length of the pattern. And as we'll see, there's ways to get around this, but for relatively small alphabets, this is no problem because the search is so efficient this way in the construction as well. But if you're doing this for Unicode for a long pattern, maybe that's too much memory to devote to the DFA representation. The bottom line is, and this follows immediately from examining the code, is that the KMP substring search is linear time. You only access at most each character in the pattern, each character in the text once. Quite remarkable. Each pattern character you access once when you're making the DFA, and each text character is accessed once when you're simulating a DFA, and that's in the worst case. Now, the space, again, is proportional to RM because we have all those mismatches. It is possible to develop a version of Knuth-Morris-Pratt that constructs the automaton in time and space proportional to M. It's actually a non-deterministic automaton because it's either a match or all mismatches, and a mismatch might involve multiple hops. So if you're interested, you can read about that version of KMP, but it's sufficiently more complicated that you should be prepared to study it carefully to really understand it. This algorithm is really interesting because of its history. It was actually independently discovered by two theoreticians and a hacker. So there's Knuth, who's one of the fathers of computer science, who read a paper that was a very, by Steve Cook, a very esoteric theoretical result that he realized implied that it should be possible to solve the substring search problem in linear time. The theorem really didn't give any way to solve it, but it indicated that it should be possible to solve it in linear time. So Knuth worked on it and figured out a way. And then Pratt, who was a student of Knuth at Stanford at the time, figured out a way to take care of this mismatch independent of the alphabet size. And in the meantime, across the bay at Berkeley, Jim Morris was busy writing a text editor. In those days, people were using typewriters, and other people were realizing that computers would be really good at editing text. And so many people would work on text editing and formatting systems. Was kind of a badge of honor in those times. But Morris actually worked for the Computer Center at Berkeley and wanted to have a really bulletproof text editor that everyone could use. And one of the things he wanted to do was avoid backup, because backup was just really inconvenient, involved a lot of code, and just something that he didn't want to have. And he basically came up with the same algorithm. And the community was kind of small at that time, and theory meets practice, and that's where this paper came from, 1977. Morris then went on to get his PhD and to work at Xerox PARC, and unfortunately later on another systems programmer came and took a look at Morris's code and couldn't understand it and put the brute force algorithm back in, but that part of the story is maybe a less successful example of theory meeting practice. That's the Knuth-Morris-Pratt algorithm, one of the most ingenious algorithms that we'll see.